we'll wait. Weizmann Institute in Israel, and he held different positions during his career, including MIT, the Weizmann Institute, also at Collège de France, and for most time he worked as a researcher at CERN in Switzerland, where until now he is an honorary member. So Gabriele is most known for his work in different parts of high energy physics, and particular string theory. So everyone who ever studied string theory knows that string theory started with Veneziano amplitude. And Gabriele also worked in other applications of particle physics. As a student, I was studying his paper about U1 problem in QCD in particular. And he is behind the creation of one of the directions in string theory known as string cosmology. So which explains how cosmology, how string theory, or trying to explain how string theory was in the beginning of everything. So today, Gabriele will talk about scattering of gravitons, scattering of quantum gravity, about puzzles in this field and in different solutions. So thank you very much, Gabriele, for accepting this invitation, and the stage is yours.
Thank you, Dmitry. So thank you for the invitation. I'm glad to be able to be virtual in Natal. Recently, I think I had an opportunity to go there for real, but somehow missed it. Now I'll try to share my screen. Let's see, it worked. Share, okay, and put a full screen. Oh, wait. Let me, well, tell me if this is okay.
Yes, it is fine. We can see everything.
Okay, so wait. So yeah, the title of the talk is From Non-Relativistic to Ultra-Relativistic Gravitational Scattering and Radiation. And the talk is based on recent work done in collaboration with Di Vecchia, Heisenberg, Russo, and earlier work with Andrei Gruzinov, Marcello Ciafaloni, Dimitri Colferai, Francesco Corradeschi. Sometimes I will use these acronyms in the following slides. Let me start with a little introduction. As everybody knows, there has been this beautiful recent detection of gravitational waves from the LIGO and then also Virgo interferometers. And this, of course, has stimulated a lot of recent theoretical work on the subject. Now, the traditional methods for computing the expected waveforms, which are needed to interpret the signals, are basically classical. There is numerical relativity, there is post-Newtonian expansion, low velocity expansion, the effective one body uh, approach of Bonan and Damour. Now, these are classical approaches, but now, more recently, new approaches, which are based on taking the classical limit of some quantum mechanical scattering amplitudes, have been pursued. Now, this fact brought together two theory communities, one from classical general relativity and the other from high energy particle physics. You know, two communities which historically were very decoupled from each other. But this generated a lot of interesting synergy. For instance, we had a very interesting and stimulating workshop in Florence, virtual though, last spring. Actually, the high energy community has been interested in the gravitational two-body problems since the late 80s, so much before the discovery of gravitational waves. For instance, in 87, there was parallel work by Toft, by our group, by Musinich and Soldate, but the motivations for that work were, of course, completely different, and I will explain below. Uh, in that context, in the scattering of two elementary particles, typically very light or massless particles, going to high energy or even trans-Planckian energy is crucial in order to make gravity a relevant interaction, because the gravitational force grows with energy, and if you want to beat other forces, you better go to very, very high energy. So the ultra-relativistic limit was absolutely necessary in the collision of two elementary particles. What we, and was actually by everybody completely missed at the time, is that even massive astrophysical black holes can be thought of as elementary particles. If you want, because of the no-hair theorem, what counts is as long as the two black holes are far apart, say, they can be approximated by point-like objects and therefore elementary particles. But of course, they are not light, they're heavy. And in that case, it's more the non-relativistic or occasionally the just relativistic regime which are relevant and not the ultra-relativistic one. However, about 4 years ago, Thibaut Damour, in the paper written there, suggested that useful input, at least for the effective one-body approach, could be obtained from this high-energy ultra-relativistic regime of gravitational scattering. And that suggestion made a lot of sense because if so, the so-called post-Minkowskian, missing, or also known as loop expansion, could then be anchored to two limiting cases. The already mentioned post-Newtonian expansion, low velocity, on one hand, and the ultra-relativistic limit on the other hand. So you could perhaps interpolate between these two interesting limits. Now, uh, a result and the puzzle at three-third post-Minkowskian order. Post-Minkowskian order means really a two-loop calculation in particle physics language. So in the papers written there, so beginning of 19, there was an impressive calculation by Bern et al. The whole set of names is at the end of the slide, which led to the first complete, quote unquote, I will explain later why the quotation marks, 3 p.m. or two-loop result. And this was for general relativity and for two massive scalars of arbitrary mass and arbitrary velocity. Now, it was checked to be consistent up to the fifth post-Newtonian order, which means v over c, velocity over speed of light to the 10, and later even to 6 p.m. order. And yet, this calculation, this result presented a puzzle. The puzzle was that the high energy, or just the massless limit of the result of Bern et al., exhibited a logarithmic divergence in energy. And this was in contrast with a perfectly finite result by Amati, Ciafaloni, and myself from 1990, so from 30 years before. Now, one should also remark that gravity is supposed to be free from mass divergences, also known as collinear divergences, unlike gauge theories. So quite some controversy came up with different solutions to this puzzle being proposed and being uh, uh, shown to be incorrect. So furthermore, both the massless limit of ACV 90 and the Bern et al. Log enhancement at large S over m square, here are the authors who gave these checks, uh, um, they not only checked those results, rechecked those results, but also claimed them to be universal. And so yet they looked mutually incompatible because one had the logarithmic divergence and the other didn't. So this created quite a lot of confusion, as I said, and the prevailing attitude for a while was that these two limits would not commute. Which two limits? The limit in which you have a momentum transfer q, which is smaller than the mass, and the limit in which the mass is much smaller than q, in particular the zero mass limit, both being, of course, much smaller than the total energy of the process. However, so this was the prevailing attitude, but the solution of the puzzle turned out to be quite different and I think more interesting. So this will be the main topic of this talk. No, okay. Now, and here is the outline. So in order to expose better the puzzle, I will review very briefly the old work by Amati, Ciafaloni, and myself, which went on for about 20 years. And then I will also discuss briefly gravitational radiation from the collision of massless particles, because this will also be relevant for comparison with the recent results. And then I will go indeed to the puzzle itself. I will first sharpen the puzzle by sharpening the old argument of ACV, and then I will show how it is solved via the so-called radiation reaction effect, And then I will describe how that radiation reaction can be computed by two shortcuts, one due to Damour from linear response, and the other one due to our group from soft theorems. And then I will have some quick remarks on computing other things like waveforms and the energy losses. And I will finish by mentioning new challenges which occur if you go one post-Minkowskian order higher, namely to 4 p.m. or to 3 loops. So this is the plan. I hope to make it in the hour or so that I have. So let me start with this quick reminder of the gravitational iconal. So the motivations, as I said at the time, 1987, were purely theoretical. In particular, we were interested in finding the emergence of classical and quantum gravity, in particular the stringy version of gravity, from some Gedanken experiments. These were thought experiments in flat space-time. And then the second, even more, and that was a reasonably easy goal. The other goal was much more ambitious, was to try to solve the information paradox. If you could check that this process led to a unitary S matrix, then of course information would be preserved even when the process is expected to lead to black hole formation. So now, so we started in 87 by considering string collisions. In particular, you can take the limit in which these strings are point particles at Transplanckian energies. And for simplicity, let's take massless string collisions. So the typical diagram you'd have to calculate, for instance, is this two-loop diagram for the scattering of two closed strings, where you can distinguish things which are exchanged, things which come in and come out, things which are produced, and so on and so forth. Now let's consider first of all the parameter space for this reaction. You have basically three length scales. Here I wrote four of them, but in string theory, if you consider weakly coupled strings, the Planck length is somewhat screened by this so-called string length, which avoids problems with the quantum gravity regime. So the other three lengths are the string scale, which is related to the string tension, the impact parameter B, which is related to the angular momentum of the process, and the Schwarzschild radius associated with the total energy of the collision. So these are three relevant length scales, and of course only ratios matter. So you can make two ratios, and this defines a two-dimensional phase diagram in which you can identify different regimes. Now, roughly, I don't want to go into further details. There are three regimes, depending on which one of these three length scales dominates over the other two. And they characterize a regime which we like to call weak gravity, when the impact parameter is much larger than the string length and the Schwarzschild radius. A string gravity where the string size is the largest scale in the problem, and that's where you see really all the string effects. And then there is a third regime, strong gravity, when you go to small impact parameter or to large energies, because it is there that classically you'd expect the reaction to lead to black hole formation. Actually, you can prove in classical general relativity that you form an horizon and therefore a black hole. So this red line is a presumed critical line for collapse once you take into account that there is a finite size of your colliding objects. Now, I will go very quickly through some of these regimes. In particular, let's start with a weak gravity regime. There, indeed, you find interesting things. For instance, that via an iconal resummation of these loop diagrams, which you can do in this high energy limit, you can restore elastic unitarity, which is violated at 3 level. You recover gravitational deflection and time delay. Although you compute everything in flat space-time, you see that the effects of an emerging shockwave metric emerge at order G Newton. And by the way, this shockwave metric was the starting point of Toft's parallel work to ours. And then later on, we managed to extend this calculation up to order G cube, which is 2 loops. That's why it becomes relevant for the later discussion. And this is the paper by us in 1990, on which I will comment later. Then there are other things. I don't want to discuss them in any detail because of lack of time. In particular, if you collide not point particles, but actual strings with some size, you find tidal excitation effects, and you can see that the process satisfies still unitarity, but this time is inelastic unitarity. The string gravity regime, I will not dwell into it, although there are many interesting results, because today we are not going to discuss strings. So, several things. So Kerr, connection with Gross and Mende, this generalized uncertainty principle, and so on and so forth. But let me go rather quickly again to the strong gravity regime, of course, which is the toughest one and where we didn't make so much progress. So in the strong gravity regime, which we only discussed in 4 dimensions and in the point particle limit, we could identify some semi-classical contributions as coming from some connected trees in a particular definition of the trees. And we could even construct an effective field theory to resum those trees after some truncation. For instance, we took only one polarization for the graviton. We reduced the theory from 4 dimensions to two dimensions. So we neglected some rescattering processes and so on. In spite of all this truncation, we saw the emergence of some critical lines in good agreement with the quantitative agreement with the classical general relativity collapse criteria, as if in this approximation you see a sign that you are approaching a collapse regime. We also made a first go at computing gravitational Bremsstrahlung, emission of gravitational waves, but we found a funny, embarrassing result, an energy crisis, because the calculation at face value gave a radiated energy which exceeded the total incoming energy, which of course is absurd. I'll come back to that. And also, unfortunately, we couldn't keep control of unitarity of the S matrix beyond this critical line or this critical surface. This was problematic. Ciafaloni and Colferai went on to try to solve this problem, but didn't get too far either. So we decided to leave it aside momentarily and turned to some simpler problems. The first one, which I will have no time to discuss today, which I did in collaborations with Apollonio, Di Vecchi, and Russo, was to look instead at string brane collisions Why that problem is simpler? Well, because the brain system is very heavy, maybe even infinitely heavy. So you approach something like the probe regime in the two-body problem, scattering from an external metric, and this is much easier than the two-body problem itself. What I will discuss instead is this gravitational Bremsstrahlung, how to improve and avoid the energy crisis when you do a more sophisticated calculation of gravitational Bremsstrahlung from massless particle collisions. As I said, in ACV 07, we got too large irradiated energy. If you have questions, please interrupt. Maybe I'm going too fast. Maybe it's too complicated. Can you hear me?
Yes, I think
Okay. Okay. Now, since
there's no
I
questions.
hear no noise whatsoever, I don't want to be talking in the vacuum. So, this is a very interesting problem, which is not yet completely solved, by the way, but I think we made quite a lot of advance. It's the question: you collide two massless particles at very high energy, P1, P2, you see, at some impact parameter B. So the angular momentum, say, goes in this direction. Uh, the impact parameter is such that this deflection angle is theta s for scattering is small, and you look at gravitational waves which come out at some angle theta and phi, and you keep theta and theta constant. So these are the approximations. Now, this process can be approached by different methods, have been approached by different methods. I will only talk and briefly about the first two. So there is a classical general relativity approach, which I considered with Andrei Gruzinov in 2014. And then there is a quantum iconal approach, which is the work I did with CC and CCC. Okay, Cefaloni, Colferai, Kuradeschi. Then there is a third approach, which uses soft theorems, which started with work by Sen and collaborators. And also I had a paper with Adasi and Bianchi on that. And what I will not show, but I will just state, is that the approach number two goes very nicely over to number one in the classical limit, which is a very nice, since these two approaches are completely different, is a very nice check on both. They also agree with number three in the overlap of their respective domains of validity. And this was particularly stressed in this recent paper by Saho and Sen of this last May. Now, the two approaches have different domains of validity, but there is an overlap. So the classical general relativity and quantum iconal approaches, at least in the what we could do, was limited to small angle scattering and also small angle of the radiation. Namely, the radiation was going mainly in the direction of the two incoming particles, but covers a wide range of gravitational wave frequencies. The soft theorem approach is not limited to small deflection angles or small radiation angles, but is only valid in a much smaller frequency region. Basically, omega, the frequency of the gravitational waves, less or equal 1 over the impact parameter. Whereas we will see that the first approach goes beyond. Now, the classical GR approach is based on Huygens superposition principle, which for gravity, unlike for electromagnetism, must include the gravitational time delay in the shock wave metric. AS is Eichelbusch-Sechsel, is a particular metric produced by these colliding particles. Now, for this approach, I only have a slide, which is a very sketchy picture, and I think it takes too long to explain it. But basically, you have something like a two-dimensional screen transverse to the collision, and you interfere waves which come from each point of the screen, like you do in Huygens approach. And but you have, of course, to put the right phase for each wave, and this consists of a geometrical uh, time delay, if you want, and also a dynamical time delay, which is the gravitational time delay, which goes like a log of the distance of the point from the source of the other wave. Okay, this impact parameter B. You see, there is one particle coming, say, at impact parameter 0. The other particle, number 2, comes at impact parameter B. So this is the impact parameter of the collision, and the generic point on the screen has a distance x minus b from the other wave, and then suffers a time delay, and you have to take all this into account. Now, I will not give the result uh, now. I will give it in a moment, because I want to, because in any case, it's the same result as you get if you do a quantum treatment in this iconal approach, which I mentioned. So in this approach, you have to sum ladder diagrams, and then from these ladder diagrams, you emit your gravitons, and you have to compute how much energy is carried by these gravitons. Now, there is a few technical details on which I will not indulge, because if I don't go into any detail, they will be completely mysterious. But at the end of the day, the result of Gruzinov and myself is exactly recovered if you take to 0 h bar omega divided by E. So the energy of the graviton of a graviton divided by the total energy. And this is the result. Okay, it's not very simple, but it's very explicit and not very complicated either. You see, this integral d2x is precisely this Huygens superposition of waves coming from each point of the screen. Here I try to define everything. The deflection angle is the usual Einstein-like deflection R over B. R is for GE. And the important thing is this phase, which takes a rather nice and simple form. Okay, now rather than going into the details of this formula, which are interesting but perhaps not so important now, let me give you the analytic and also some numerical results which come out from this formula. So the analytic results can be summarized by saying that the spectrum of the emitted gravitational waves has a Hawking knee and also an unexpected bump, which is quite nice. So the knee first. To explain what is this Hawking knee, I'll tell you first that if you look at the energy spectrum, gravitational energy spectrum per unit frequency, in the range 1 over b to 1 over r, remember we are at small angle, that means r over b is small, so b is much larger than r, so there is this range between 1 over b and 1 over r, where we can do our calculation, no problem, and we find that the behavior of the of the spectrum is this. It's almost constant. There is only a logarithmic dependence on omega. The minus 2 is of the argument of the log. There is not log to the minus 2. So now, however, this doesn't go all the way down to omega equals 0. If you are at omega smaller than 1 over b, then it freezes at the value when omega is 1 over b. And when omega is 1 over b, you get r over b, but r over b is the deflection angle. So that's what you get. And this result, the zero frequency limit of the gravitational wave spectrum, is well known and is called in jargon ZFL, or zero frequency limit of the spectrum. It goes back to work by Smar in the 70s. And this fits very well so with all the expectations. Now, what is new is that if you go above 1 over r, so then all of a sudden this logarithmic drop of the spectrum becomes power law, becomes, you can say, scale invariant. It doesn't mean much. So d omega goes like the scattering angle squared times E over omega. Okay, so you get a spectrum d omega over omega, a logarithmic spectrum. And the Hawking knee, why is the Hawking knee? Because 1 over r would be the typical energy of a Hawking quantum if you had formed a black hole of radius r. Okay, so we call it the Hawking knee. This is, for instance, some numerics, which shows what I was saying. You see here, you get this 1 over omega behavior. And at smaller frequencies, it flattens out, and you reach this zero frequency limit for different values of theta. There is this log theta dependence of the ZFL. So this fits really with what we want. Now, there is a problem still, because if this omega 1 over omega spectrum goes on up to infinity, you still get a divergence, okay? If you integrate the spectrum over omega to get the total yield, the total energy yield, you find a logarithmic divergence, which is much, much milder than the previous energy crisis divergence, but it's still a divergence. So you have, if you put a cutoff on omega at some omega star, then you get a logarithmic sensitivity to the cutoff. Now, with some motivations, which again, I don't have time to explain, in the paper of Gruzinov and myself, we argued that this omega star inverse powers of the scattering angle. So if you want, is b squared over r cubed. And then in that case, of course, the total efficiency or the total yield of energy will be over the theta square log theta square, which is now perfectly fine and small for theta small. We even argued with Gruzinov that above this omega star, the spectrum should start falling like 1 over omega square. And then we learned, actually we learned from Giat Valley, that such a spectrum, 1 over omega square, turns out to be that of a time integrated black hole evaporation. If you let a black hole evaporate a la Hawking until it dies, and you integrate all the spectrum, you find that the spectrum goes down like 1 over omega square. Um, so, okay, keep this in mind. This is still not a finished problem because one would like really to know what happens at high omega and high frequency, and we'll see something similar will come back in the end for the actual problem, physical problem of the scattering of two black holes. Okay, now I told you also that there is a bump. How is time going? Quickly. So I will go very quickly on that. You see, here I wrote again the, the spectra as small omega b and at large omega b, but smaller than omega r. This would suggest a monotonic interpolation. Well, we found that actually there are logarithmic corrections to this and the small omega b region, which lead uh, to a tiny bump. You see here, you can hardly see it. If you blow up the picture, you see that the spectrum has a bump. We were expecting a monotonically decreasing spectrum. Well, that turns out not to be the case. So there is this little interesting bump. But I think it's okay. It's mainly a curiosity. It has also been confirmed by these soft graviton techniques. So I think it's a solid result, but it's a tiny bump and difficult probably to measure if you can. Okay, there are other numerical results, but for this I refer to the literature. So let's go to the what should have been the main topic, which is the massive iconal for black hole encounters and mergers. As I said, we could have hardly imagined such a connection some 30 some years ago. So so first of all, we sharpened the 3 p.m. puzzle that I mentioned at the beginning. And this you can do. So there was this argument given in ACV 90, but we had to extend it to the case of massive particles. For instance, if Q is smaller than M, and also in some more general situations. And the basic tools were real analyticity of the scattering amplitude, crossing symmetry, and the asymptotic behavior at each order in perturbation theory, which gives rise to some suitably subtracted fixed T dispersion relations. And from those, you can get informations on the high energy limit of the ratio between the real and the imaginary part of the scattering amplitude, in analogy with what was done long ago for high energy soft hadronic physics. It was very popular when I was young in the 70s, and it's now again popular with the high energy LHC data where people fit, cross elastic and total cross sections. So using these tools, we could prove the following. Now, first of all, some definitions. The S matrix in energy and impact parameter is written as an iconal phase, exponential of an iconal phase, which is then expanded as delta 0 plus delta 1 plus delta 2, where delta, where delta n is avoided g to the 2n. Now, 2n plus 2, no, g to the, well, I cannot read it. So, if the imaginary part of the amplitude goes at some order as, or in some diagram, like s to the n times log s to the power p, then those analyticity arguments allow to express the real part of delta in terms of the imaginary part of delta, plus other contributions from lower order calculations. So at the end of the day, you get this quite interesting formula relating, because remember, at two loop, we are interested in delta 2. Now, if you can express real delta 2 in terms of the imaginary delta 2, then you can hope to estimate the imaginary part and get the real part just from this relation. Now, you see that this relation depends quite crucially on this power p appears in the log s. The power n is fixed, and so it's easy to take care of. But the powers of logs are a little bit tricky, and as we will see, that's really where the puzzle came from. If p is generic, for instance, p equal 2, say, then this non-universal quantum piece, it turns out that this is not a classical piece, intervenes in the final result and makes it dependent on this non-universal piece. Furthermore, since neither im delta 1 nor delta 0 have log s, if im delta 2 does not go like log s, namely if p is not equal to 1, then at the end this term can blow up or go to 0 and so on. And in fact, if you take the result of Bern et al., you convert it in this language, it corresponds precisely to p equal 2. If p equal 2, the imaginary part of delta 2 uh, will go like log square, and then the real part goes like log s, which is precisely the origin of our paradox. On the other hand, if p were equal to 1, then real delta 2 will not depend on this non-universal term, approaches a finite ultra-relativistic limit because the log s cancels here, and the above relation simplifies and gets this very simple formula if you take p equal 1. Now, the logarithmically growing terms in im delta 2 actually has an infrared divergence, which, however, cancels against a similar infrared divergence which is there in delta 0. So in the end, you can show that this produces a perfectly finite result. But you see, you need p equal 1, whereas Bern et al. Had p equal 2. Sorry. So in order to understand whether p is 1 or p is 2, we had to relook into the three-particle unitarity cut of the two-loop amplitude, which is directly related to im delta 2. So this is the cut, okay? You take a 2 to 3 amplitude, you square it, and you put on shell the intermediate states, and you try to do the integrals. This was done already in ACV 90 for 0 mass, and we have redone the whole calculation for a generic q square over m square ratio. And we found that the answer is a single log and not a double log like Bern et al. So, so if you then work out the whole machinery, you put p equal 1, you put your results for im delta 2, the ones for delta 0 and delta 1, which we know already from lower order calculations, you crank the machine, you obtain exactly the ACV 90 result. But now the clash between ACV and Bern et al. Looked more and more puzzling because, okay, on the other hand, the result of Bern et al. Had been checked. And so where is the problem? Well, we decided to compute the full amplitude in n equal 8, not just this imaginary part, okay? And we used modern techniques which go under the name of integration by parts and differential equations. But most crucially, we included contributions from the so-called soft region of integration, where, say, the gravitons can carry enough energy, okay, can be on shell, basically. And we found that at high energy, the sum of some planar and non-planar boxes gives a contribution of the same order as the one coming from the H topology. What is the H topology? Sorry. You see, this diagram, when you close it, looks like an H diagram. And Bern et al. Computed this H diagram. However, is a little tricky. One thing is the Feynman diagram, okay, which is just shown here, and the other a different thing is an H diagram meant as the full 2 to 3 amplitude squared, okay, where the emitted graviton K is not necessarily emitted from this exchange graviton, but can be also emitted from the external legs. Anyway, this is just technicalities. When you take into account these planar and non-planar boxes, you find that they also go like log square s, but they precisely cancel the, the other contribution, and and then uh, and then you remain with a simple log s in imaginary A2, and the log s term in real A2 also cancels thanks to this general argument. And this was finally confirmed also by others. And this is what comes out of the full calculation. If you want, this is the, okay, the calculation was done first in supergravity because it's simpler. There are fewer diagrams, there are many simplifications. So that's where we did this first calculation. In the case of n equal 8 supergravity, there was a paper by Para-Martinez, Roof, and Zheng who found this result. Okay, it's simpler again than in general relativity, and it's just this. But you see, this cosine, this arcs cosh sigma is precisely what gives the log. This is the logarithmic divergence. So if you keep only this term, there is a logarithmic divergence. What we found from this soft region are these two extra terms. One which exactly cancels a large sigma. You see, sigma is a standard notation, and it's proportional to the energy. So you have to send sigma to infinity to go to the limit of s over m squared large. And you see that these two terms precisely cancel as sigma goes to infinity. So the logarithmic divergence becomes subleading, and this term dominates, and turns out to give the ACV result. You can also reformulate all this in terms of the scattering angle, and you have a similar discussion of what cancels what and what remains. But you see, this is basically what remains, whereas these two things cancel. Now, when we presented this result at an Albert Einstein Institute meeting in a little over a year ago, Thibaut Damour immediately grasped the physical meaning of what we had found. Our new terms, unlike the previous one, had a half-integer post-Newtonian expansion, which means, in other words, an expansion in odd powers of the velocity and not even powers of the velocity. So the checks that people had done so far on the Bernoulli result were only dealing with the integer Pn terms. So and they found agreement. But, these odd terms are there too. If you go back to this result, I mean, a small velocity means sigma going to 1. And you see quite easily, you see that this term for sigma goes to 1 has an extra square root relative to this. And sigma minus 1 is v squared, so the square root of sigma minus 1 is v. That's how you see that these new terms have the opposite parity in terms of powers of v. Now, sorry. So these new terms are like the previous one, and that meant that we had added to the conservative dynamics of Bernoulli's calculation the effect of radiation or the so-called radiation reaction. These odd powers of B mean that a process which is not time reversal invariant and it's related really to radiation damping. So, and in fact, Damour immediately jumped on the subject and managed to find a shortcut to compute this radiation reaction, if you want, extending our result to general relativity. We had it only for n equal 8. So this is the work of Damour, which uses a nice trick, namely he used the previous result with Bini relating the radiation reaction to angular momentum loss. And then he argued that at 3 p.m. order, the order at which we are dealing, only the angular momentum loss, which enters at order g square, is important. He managed to compute this order g square radiated angular momentum, and in this way he got the 3 p.m. radiation reaction correction to the Bernoulli deflection angle, recovered smoothness, and even this universal ACV 90 ultra-relativistic limit. And since then, the result by Damour has been confirmed by at least 2 different techniques and also the brute force calculation. Well, perhaps for lack of time, I will also skip another puzzle. There is a minor puzzle which comes out of the Damour argument, which has to do with what's the true J angular momentum which is radiated and what is the relevant angular momentum which is radiated, because one can ask, how can one radiate angular momentum at order g square without also radiating energy at that same order in g? This looks puzzling, at least to a particle physics person like I am at the quantum level, if one associates the loss of energy and angular momentum with the energy and angular momentum of the emitted gravitons. And with Grisha Vilkovitsky, we have been looking into this, and we have a paper, under preparation for many months. It's still being written, and I don't want to spend time because I don't have time, but I think we understood what is the true angular momentum loss, and it is of order g cube, not of order g square. But then we also think we understood what is the relevant j rad, which is not the physical radiated angular momentum, and this is the radiated angular momentum in quotation marks that enters the Bini-Damour formula. So this justifies Damour's result. But I will skip on this. You can ask questions if you want. So On the other hand, we had also our own shortcut to arrive at a radiation reaction, and this goes again through using analyticity and crossing, because we found that the radiation reaction contributions is directly related to the soft behavior or the infrared divergent part of the amplitude, because we found that the real delta 2 and imaginary delta 2 always appear in the result in a particular combination. By playing with this, we arrived at a very intriguing or somewhat surprising formula, which relates directly the radiation reaction, so the real part of delta 2, which is what gives the deflection angle, to, you see, the spectrum of gravitational radiation in the zero frequency limit. Remember, we discussed the zero frequency limit a lot previously, this CFL, which is well known. So in this way, we could recover also the radiation reaction very cheaply. Um, and for instance, we have rederived the Moore's result in GR, computing directly not the deflection angle, but the phase shift. And you see, it's a rather complicated beast, but um, but you see, all these terms combine quite nicely to give the ACV result. Um, we also rechecked our n equal 8 supergravity result, the radiation reaction for n equal 8 supergravity. Here, while the result is simpler for supergravity, if you do it with this formalism of radiation reaction, it looks more complicated, because in n equal 8 supergravity, you don't just emit gravitons, you emit gravitons, dilatons. There are two vectors and two scalars in the particular version of n equal 8 supergravity that we are considering. And each one of them contributes to the radiation reaction, another complicated terms. But when you add them up, you get precisely the, the result we got from the direct calculation. Okay, last two slides, very quickly, waveforms and energy loss. Many groups are still working on the waveforms. There are several already, however, interesting results available. No time for that, sorry. It's, however, instructive to compare instead the energy loss with what I mentioned for the massless ultraviolet limit. In fact, there is a result, a very beautiful result by these people, Herman, Paramartinez, Ruf, and Zeng, which, however, leads again in the ultra-relativistic limit to an energy crisis, which is very similar to the one found in ACV 07. There's also a warning by Kovacs and Thorne about this. Anyway, so it seems that again, a resummation in powers of G, as in the work I described, appears to be necessary. So I just flash the result of these people, which has been double checked and confirmed also by our group. You see, again, it's a rather simple formula for the total energy radiated in the collision of these two particles with mass. It has a prefactor and then factors which depend on this sigma, which is S over m squared, large energy. And when you, well, for n equal 8, it's simpler. For GR, it's more complicated. But in both cases, E radiated divided by square root of S, which is the total available energy, goes like theta cube times square root of this sigma, where sigma is S over m squared. So you see, if you keep the angle fixed and you send S very large, you end up with a crisis again. So hopefully this will be solved by similar techniques as the one we solved for the massless case. And finally, I want to mention new challenges if you want to go to higher order in the post-Minkowskian expansion, namely to 3 loops. There is already a partial result, which has been published by Bern et al. In beginning of this year. The long paper is still not written, unfortunately, so many details are still missing. And unfortunately, it exhibits the same shortcomings of the 3 p.m. conservative result. So now they are aware that this is only the conservative part, so they stress this. However, the shortcomings of the 3 p.m. results are now worsened in the sense that not only the ultra-relativistic limit is more singular now than at 3 p.m., it diverges like a power, for instance, of the inverse power of the mass. But even if one goes at finite energy, the result is infrared divergent. And the infrared divergence, the coefficient of the infrared divergence is related to the, as expected, to the 3 p.m. energy loss. Therefore, at 4 p.m., adding radiation reaction, which is in classical general relativity is called the tail contribution, is absolutely essential to recover a finite result even at finite energy. This is a hard problem. Several groups have been working on this, including ourselves. But I think, as far as I know, nobody has finished this complicated calculation. But as I say, it's essential if you want to get a finite result. So my summary, we have seen how including the full soft region allows for the iconal phase and therefore the physical scattering angle, including radiation reaction terms, to be continuous function of the velocity from v equals 0 to v equals 1, so that Newtonian and ultra-relativistic classical limit get smoothly connected. We have also found this intriguing relation between the radiation reaction terms and the order G cube zero frequency limit of the energy radiation spectrum, which itself is controlled by soft theorems. So that's a very nice simplification at this order. And this looks mathematically equivalent to Damour's connection, which uses this linear response and radiated angular momentum. We have not understand the precise physical reason for the agreement between the two. Now, I stressed at the end that taking care of radiation reaction becomes essential even away from the ultra-relativistic limit from 3 loops or 4 p.m. on. It is an important and yet still challenging problem. Eventually, we would like to construct a unitary S matrix, at least in the semi-classical approximation, from which then we can extract all sorts of observables that have a classical limit, including dissipative effects like energy loss, radiation reaction. To this purpose, the iconal phase is no longer sufficient, should be promoted to an emission operator so that the S matrix is unitary, and then that emission operator itself should be expanded to the desired order, should have its own loop expansion. And this is work in progress. I thank you for your attention.
Thank you very much, Gabriele, for this very nice introduction and the gravitational scattering and gravitational radiation. And we can pass to questions. So if there is any question, please raise your hand or write your question in the chat. So I'll probably ask the first question. So first I would like to clarify, so basically your work showed that the work of Bernal was not complete because they were considering only conservative contributions and they were not considering energy loss or environmental loss situation. Is it correct that what in particular when you mentioned the next the fourth order, is it correct that well, including this radiation effects, you're able to solve additional divergences?
Well, you mean at the next order, you say?
Yes. Well, actually either order, so I'm not sure I understood this in the
yes.
level.
Well, yes, thank you for the question. I'm sorry also that I had a bit too much material, so I went faster than, than I should have been. So at 3 p.m., so at 2 loops, the radiation reaction is now fully under control, and it gives a finite result at all energies and a smooth connection between the non-relativistic, relativistic, and ultra-relativistic regimes. If you do not include the radiation reaction, if you only take into account the conservative part, then there is this logarithmic divergence at high energy. But also, you see, at finite energies, there are all these post-Newtonian corrections with odd powers of velocity, which in principle are there. Now, the defense of the conservative school, if you want, of Bern et al., is to say, well, we are not really interested in the physical deflection angle. We are interested in fixing the conservative part of the process as an input, for instance, to the effective one-body approach, which then will add separately radiation reaction, dissipative effects, and so on. What I'm saying is that if, okay, first of all, that the deflection angle computed from the conservative dynamics is not the physical one, okay? And second is that if you take a particle physics approach, then, and you don't restrict the integration region artificially to the so-called potential region, then you get everything in one shot. And furthermore, the whole process is Lorentz invariant, crossing symmetric, and so on. Whereas if you do this, if you limit yourself to this potential region, you break Lorentz invariance, and so on and so forth. However, okay, so, but then you can say, okay, at this level, it's really a matter of taste, if you prefer to do the full calculation at first, or do the conservative and then use it as an input to something else, which then will add the dissipative effects. What I'm saying is that at 4 p.m., at 3 loops, it becomes absolutely important to include these terms, because otherwise the answer is divergent. It's just infrared divergence. If you do dimensional regularization, there is a nice 1 over epsilon sitting there. Okay, nonetheless, I must say, some people, like the group of Bonanno, has used already this result, neglecting this infinite term. But you know, this is very dangerous. You take an infinite term, you just throw it away. You know very well that you may be throwing away some finite piece as well, together with the infinite one. So I think, at least conceptually, it's very important to understand how exactly this infrared divergence is cured. Everybody thinks that it's cured, by the way, by this radiation reaction. But what are then the finite terms? I can more or less see how to cure the divergence, but I'm not sure how to compute all the finite pieces. That's the problem. And I don't know. Maybe Ricardo has a has found a way in his language. There is Porto, who has his own approach, the group in Caltech. Uh, I think we are all trying to go for this three loop result. And as far as I know, nobody is there yet.
I think Ricardo raised his hand. Maybe he has a solution already. Please
Yeah.
go ahead, Ricardo.
Yeah, actually, about this finite piece that come from infrared divergences, then when you that cancel when you add longitudinal modes and radiative modes in our language. No? So this is a problem that we start hitting 10 years ago, actually, in the post-Newtonian language. In the post-Newtonian language, people first realized this 10 years ago, and we computed the finite piece that come along with the propagation of modes that can go on shell. So internal modes that are not only longitudinal but can go on shell. They give a finite piece, and this was a famous number 41/30 that looks like a pedantic thing, but it was a huge success of the method because it was checked with extreme mass ratio. So at 4pn, so 4pn means up to g to the 5, whereas 4pm means up to g to the 4. So at 4pn, for post-Newtonian, up to g to the 5, the issue is completely settled, and we know what is the finite piece, and it has been confirmed by extreme mass ratio result, so nobody doubts about it. Now we are at 5pn. At 5pn, there is still some discrepancy, but I mean, we are working on it actually with the student is here in the call as well. And we believe that we can sort this out, at least the disagreement with the extreme mass ratio. So in the post-Newtonian, we knew that the internal propagation of modes can go shell do give a finite piece, and in principle, we have computed it. But in the post-Newtonian, we compute a different observable. Actually, we don't even compute an observable. We compute the effective potential, which is not even observable. It's the force, which is unobservable. And things fit nicely there, apart from some discrepancy at g to the 6. But it looks like some technical discrepancy. It doesn't look a fundamental.
Yeah, I have seen papers. Yeah, I would say that they get a slightly different result. Also, Damour has done work on that, right?
Yes. I mean, we are working to smooth out this discrepancy, but it doesn't look to be fundamental. It looks like something technical related to the fact that when you define the epsilon you use a dimensional regularization, but then there is a Levi-Civita epsilon, so it's a bit tricky to define the Levi-Civita epsilon in the dimension. So it looks really something technical. Whereas you're computing a different observable, no? The scattering angle. So up to 3pm, which is g cube, people were supposed to be safe because basically using the equation of motion, you can throw the effect of modes going on shell to g to the 4. That's why Bernet al, I mean, what you were saying, I'm just rephrasing in a different language. They just said, okay, we are looking only for the internal propagation of longitudinal modes, of potential modes, just because those ones, they enter g to the 4. You said that enter with a v square, with an extra v square, but by using the equation of motion, you can trade a v square with an extra g in circular orbit, of course. In unbounded scattering, no. Basically, since they were thinking of the application of bound orbits, you can do this trick using the equation of motion and throw it to g to the 4. Of course, if you want to do, because at the end of the day, in the back of their mind, they were thinking of the application to waveform for bound orbit rather than.
That's who I should have said that, right? Of course, the more.
But you're completely right, of course. I mean, the effect is there, and for bound orbit is g cube. But at the end of the day, if you want to apply to bound orbit, is g to the 4, and that's the stumbling block for them to compute these integrals, this post-Minkowskian integral at g to the 4. We compute the same integral at g to the 4 in the post-Newtonian because in the post-Newtonian, the post-Newtonian framework give us some simplifying assumption, and then we can compute the integrals more easily. Whereas they have the difficulty that the integrals are very difficult and have been computed only in the with Feynman boundary condition, not with retarded advanced boundary condition. And so basically they have computed some new integrals that nobody ever computed before. We, in the post-Newtonian, we could recycle things that have been already done in particle physics. And so basically the post-Newtonian is a simplified version, but we're computing again a different thing, the effective potential, not the scattering angle. So there are, we could go further, but we are computing different things, and we could recycle more tools of particle physics.
I see. Well, is your feeling that to go to all orders in V, but fixed order in G, it's harder? I mean, if you
Well,
want
yeah,
the 4
yes,
PM at all orders in Pn, that will be hard.
that will be hard exactly for this, because basically we are not doing that, but those who
No,
are
I
doing
know.
that have to compute this new master integral. I mean, the master integral which wouldn't be new if it was with Feynman boundary condition, but with the retarded boundary condition is new.
I see.
And we don't even know if it's computable. I mean, maybe it is. People are actually trying to compute first the Feynman and then estimate the difference, like Raphael and other people are trying to do this.
Okay,
But
that's what they
Raphael
do.
told me, yeah, he told me that he was on it last year. He hasn't published on it yet, so it must be hard. But I
Yeah, it
haven't
must
tried.
be hard. I mean, people have started to think about it long ago, and it's still we are still waiting for results. No, I
Yeah, in the
mean, yeah. The other thing is that this infrared divergence is related to the energy loss, and if you go to a very to an ultra-relativistic limit, we have seen that the energy loss itself is a bit tricky. So I don't know. It could be that that that, mm, that in this case the ultra-relativistic limit is prohibitive. Of course, it's not very interesting from a physics point of view, but conceptually, I would have liked to have also at 4 p.m. a nice smooth limit. Uh, till the
yeah, of course, but
ultra-relativistic one.
one
But
should
it could be done, could be difficult. I don't know.
one should do all the possible consistency checks, because at the end of the day, one is picking up just numbers, and can you be sure whether the numbers are right if they don't have the consistency?
Recording stopped.
Uh, uh, the S method should be written as an operator as soon as you want to describe inelastic processes. In fact, one example of that we have already when we scatter strings on strings. I had to skip that, but what we did there was precisely that, to write the S matrix as the exponential of an Hermitian operator, which acts on the space of string states. So that quantum mechanically, you start, say, with two massless strings, two gravitons, for instance, and then these operators induce transitions in which the graviton gets excited into a massive string. And there we managed to find, for small deflection angle only so far, but it's a completely unitary S matrix. But it's an operator, it's no longer e to the a phase, okay? So now, forgetting about strings, but now thinking about Bremsstrahlung, emission of gravitons, will be, I think it's necessary to think about the S matrix as an operator, at least in the space in the in the Fock space of the gravitons. Of course, we don't want to touch physically the two black holes. The two black holes are not going to be pair created or anything like this. But in the graviton space, and actually in papers with Ciafaloni, Colferai, we have these operators. By the way, they should give coherent states of gravity. So what is a gravitational waves from a quantum mechanical point of view? It should be not a single graviton, not a few gravitons, but many, many gravitons. In fact, you find typically that the number of gravitons which are emitted in the process is of order 1 over h bar. So diverges in the classical limit. But, for instance, the energy carried by the gravitational wave is h bar independent because it's h bar omega for each graviton times the number of gravitons, which 1 over h bar. So that's how, for instance, you recover that the energy emitted in gravitational waves approaches the classical limit from a quantum mechanical point of view. But for instance, if you ask the question, how many gravitons you produce, this is not a question you can ask classically. But this coherent state created by my S matrix operator will tell you also that, okay? Will count how many gravitons you have. So in that sense, I think would be very interesting to construct this S matrix operator, at least in this semi-classical limit in which, say, what sits in the exponent is of order 1 over h bar. You know, think in terms of a WKB approximation to the wave function is typically what sits in the exponent is a classical action divided by h bar. So in that same spirit, one should construct the S matrix. So that's what I had in mind. No, not an Hamiltonian. Well, in a sense, it is the Hamiltonian because the S matrix is the evolution operator, and this is related to the Hamiltonian of the system.
Well, thank you very much again. I was a bit, my internet was out for a few moments, but I'm back. So we're a bit late, so let us accept one last question from Gabriele. Gabriele, please go ahead.
Hi, hello. If possible, I'd like to know more about the puzzle that you're saying, that you mentioned, regarding the angular momentum losses that the wave is facing,
okay.
if possible.
Okay. Yeah, well, okay, I can, maybe I share screen again, then, how was it, like this? Let me, can you hear me?
Yes, and we can see your screen.
Yes.
It's not yet on full
I'll
screen.
put maybe full screen. Yeah, it will be rather quick, I guess. So, yeah, this is the, so this is what we are saying with Wilkowski. So the definition of angular momentum and of its loss in GR is affected by ambiguities. This is well known. It's a well-known problem. There is a lot of literature on this. This is related to the possibility of performing these BMS, Bondi, Metzner-Sachs transformations. So in this Bondi-Sachs formalism, you write a metric in these Bondi-Sachs coordinates and you identify the the sources of the gravitational waves in some components of the metric, or which is expanded at large distance. However, by performing this BMS transformation, you can change certain things, and in particular, you can get rid of the shear of this metric. Okay.
Things have changed
Now,
since we last saw
people
each
who
other.
experts of this, like Ashtekar, say that there
Since we
is a
last saw each
canonical
other.
Bondi frame in which, if you want, in the far past, you get rid of this shear through a
I'm going to give you an
BMS
overview of the
transformation.
course.
And
Why we
with
study anatomy.
Wilkowicki, it's quite easy. You can take the result of Damour, okay, his formula for the angular momentum, and you can gauge it away. So it's very strange. I mean, since his whole effect on radiation reaction comes from this order G squared term in the angular momentum loss, if you can gauge it away, you can ask what is the meaning of this. In fact, if you sit in this canonical Bondi frame, then the angular momentum of the system in the far past coincides with the ADM angular momentum, if you know what I mean. And then when you compute the loss, the subsequent loss of J, it comes out over the G cube, just like the loss of energy, okay? So from that point of view, it smells very bad for Damour. Says, what is he doing? I mean, his order G squared J is fake. However, we found another Bondi frame, because there are infinitely many of them, which we called intrinsic. Actually, I wanted to call it barycentric, but I don't know. Wilkowicki didn't like it.
Biceps bracky.
With the properties that the light cones of this Bondi frame coincide asymptotically with the light cones which originate from the word line of the center of mass of the system. So it's a rather special
Gluteus maximus.
Bondi-Sachs frame. And so we believe that this is the reason why the Bini-Damour formula should be used with that J rad computed in this gauge. And in fact, as a double check, we found that the J rad computed in this other Bondi frame is precisely Damour's J rad. I'm not completely convinced that the formula of Bini-Damour needs this gauge. I mean, Wilkowicki is more convinced than I am, but certainly there is this interesting connection that the J rad of Damour, the one which produces the correct radiation reaction, is the J rad computed in this particular Bondi frame, which has this particular property. I don't know if this give you roughly the picture.
Okay, thank you very much.
Yes, I think it was a very detailed explanation. Thank you very much, Gabriele. Before closing this session, let me just mention that we also have a YouTube translation of the seminar, and there was a message for you from Itzhak Bars. I'm not sure you know him personally, but he was just saying hi to you and thank you for an interesting seminar.
Okay, thank you.
So thank you very much once again for accepting our invitation for the nice seminar, and thank you everyone for participating, and we'll have more seminars next week.
Very good. Good luck for everything.
Thank you.
Thank you again.
Thank you. Thank you.
Bye bye. Thank you.
Bye.
Bye-bye.
Shall I send this a PDF? Do you keep? Or you
No.
record it anyway?
Yeah, we record it and
Okay, so
it will
you
be on
don't need the
YouTube.
file. You don't need the file. Okay.
No.
Okay. Good.
Thank you.
Thank you. Bye bye.
Ciao, Gabriele.
Bye bye.